well, here we are at section 7.3. We're looking at a new conic section called the ellipse. Some people want to call it an oval. Well, okay. Alright, so by definition, ellipse is the collection of all points in the plane, the sum whose distance is from two fixed points, called the foci. Now we have two focal points, is a constant. So what that means is this d1 plus this d2 always has to be the same constant sum, no matter where this p is at. And you may have done this assignment once. Let me back that up there a bit. You might have done this when you were in middle school. You probably took an XY plane in math and you did this on a cardboard and you stuck a pin at this focus point, a pin here at this focus point, tied string to it, put your pencil in there, and kind of held it somewhat reasonably tight, and then you traced it all the way around to here, put your pencil on the other side, and you trace it all the way around to here, and you do the top half and the bottom half, and you draw yourself an ellipse. All right, so let's talk about some of the distances that we're going to look at, specifically with from the center of the ellipse to the foci, to the vertex, to the little v, which I'm going to call a covertex. All right. Before we get started, though, with discussing anything, there's something called the major axis that connects the two vertices, the capital V's. Sometimes you call these the major vertices, and your minor axis connects these two smaller letter V's. And again, sometimes they're called minor vertices or covertices to match the name of the axes. But your distance from the center to the foci, we're going to call that C. So this point F will be at negative C comma 0. This one will be at positive C comma 0. So that's this segment right here. So foci to foci is a distance of 2C. C plus C. Next, we're going to look at the distance from the center to the vertex. So that's all the way out here to these capital V's. We're going to call that A. So this vertex here is going to be at A comma 0. This one would be at negative A comma 0. And that whole distance across A and A would be the length of 2A. So your major axis is 2A. Next, we're going to look at the center to the covertex or minor vertex. That's going to be a distance of B. So this little point up here at little v is 0 comma B. Down here, we're at 0 negative comma B. And if you will, that's 2B and a B. So add those together would be 2B. That's the length of the minor axis. All right, so what we're going to do is use these A's, B's, and C's to help us find this sum. So let's pretend we were to take this point Px, d1 plus d2, and slide it along the curve until it's right in the same spot as this vertex. So therefore d1 would go from this focal point all the way to this vertex. And D2 would be this short little segment right here. That's D2. So we've got to add those two together, and that's going to be your constant sum. Well, because our focus, starting here, goes through the center, there's a C, and then the center to the vertex would be a distance of A. So D1 is C plus A. D2, well, that really doesn't make it to the center. However, we can say A, vertex to center, minus center to focus, minus the C. That would be the distance of D2. So again, A is from the vertex, or where your point P is at, to the center. The distance of C is from the center to the focus. So you subtract that away from A, you're left with this little chunk right here, D sub 2. So if we add those two together, C plus A minus C, the C's are going to cancel, and your constant sum is 2A, which is the same as the length of the major axis. So again, you could also see that as, remember, here's D1 from this focus point all the way to this vertex. Well, think about taking this little green segment, chop it off, and put it at this end, and everybody's connected together, and that's the length of the major axis. All right, the next thing we want to look at is that there is a Pythagorean triangle relationship here. So again, let's take point P. I was going to say move it up to the top, but there's already a triangle up here. Let's continue moving it all the way down to where this little co-vertex is at. So here's D1, here's D2, but what happens now is you technically form an isosceles triangle. These two legs have to be the same. So now D1 and D2 have to be the same. Well, wait a minute. We just said that the major axis and the constant sum is the same thing. So if these two sides are the same, hey, come back here, then they both have to be a distance of A. If the constant sum is the same as the major axis, and these two distances are the same, each one of them is an A. So now, here's my right triangle. Using these, wait a minute. Isn't our Pythagorean theorem usually having C on the hypotenuse? So we're just going to have to adjust here a little bit. My Pythagorean theorem has A on the hypotenuse, so it's going to be A squared equals B squared plus C squared. Oh, Lord, I know I'm going to get that all messed up. So here's what we like to do. We really would rather have this as C squared by itself. So if you subtract over the B squared, it's A squared minus B squared equals C squared. So we call it the Pythagorean theorem with a minus sign. And that's the relationship of the three distances for A, B, and C. All right, for graphing purposes, what we're going to do is you are going to start with your center. You'll count A units in either direction, left, right, or up or down, and that will be your major axis. And then you'll count up or down the length of B to get your minor axis. And that's all going to be given to us in our equation. So looking at what we call a vertical ellipse and a horizontal ellipse. Vertical means the major axis stretches up and down. Horizontal, the major axis stretches left and right. Okay, so if we are centered at the origin, and I have x squared over x squared over b squared plus y squared over a squared, and it's equal to 1. So technically what we've done is taking the equation of the circle, x squared plus y squared equals r squared, divided over the r squared, and there just happen to be coefficients here that we had to reduce, and we get two different values on the bottom. Now, A has to be bigger than B, and B has to be bigger than 0. No negatives here. And since A squared is located underneath y squared, then from your center, you'll count A units up, A units down. And since B squared is located underneath the x squared, we're going to count left and right with a B. So left and right B, and then we're going to draw in our best oval shape for our ellipse. If we're looking at a horizontal ellipse, notice now the a squared is underneath the x squared. B squared is underneath the y squared. So now I count left and right A and up and down B. Where that A is located, again, it's the biggest value underneath the x. You count left and right like the x-axis. And if we want some ellipse where our center is at HK, again, notice there's just the H and the K being subtracted from X and Y. All right? And notice that they don't change position. Only the denominators switch, because a squared is always representing the bigger denominator, bigger value. All right, time for graphing. No minus h, no minus k, so our center is at the origin, 0, 0. Plot that point. Now, one thing I encourage you to do is like, hey, here's 25 underneath the x squared. That must be my a squared. It's the biggest. So the square root of 25 is 5, but I like to put the plus or minus, and I also like to draw an arrow left and right, telling me the direction in which to count because I'm underneath the x-axis. And b squared is 16, so the square root of 16 is 4, plus or minus 4, I count up or down. So from my center, left and right 5, up and down 4, and we draw our best looking ellipse. Now, the other thing you're going to also have to plot or identify their location is the foci, and that's the distance of C from the origin to the foci. So we grab that Pythagorean theorem with the minus sign. We have a squared, 25. We have b squared, 16. We just plug it in there. So basically, you're just subtracting the denominators, big minus small. 25 minus 16 is going to be 9. The square root of 9 is 3. So we're going to count left and right 3, plot that point, and give it a capital F by its point to identify the foci. Foci always head out towards the capital V's, never towards the lowercase v. And that's how we graph an ellipse. Now, sometimes you might be given this equation and they just ask you to identify the coordinates. So what are the coordinates of the vertices? Well, you know you're starting at the origin, 0, 0. You've got this plus or minus 5. It's going left and right. You just add it and subtract it to the 0 on the x-coordinate. Your vertices are at plus or minus or positive, negative 5, 0. If they want to know the co-vertices, take that plus or minus 4, add it to the y-coordinate of the center. There's your co-vertices. If they want to know your foci, where are they located? That's that distance of C. Add and subtract that to the x-coordinate of your center. Plus or minus 3, 0. All right, next example. We have x squared over 4 plus y squared over 25 is equal to 1. This is ready to go. Now my a squared is underneath the y. So again, no minus h, no minus k. The center is at the origin. Square root of 25 is 5. We're counting this time up and down 5. So up 5, down 5. There's my capital V's. 4 is underneath the x squared. We're counting left and right. The square root of 4, which is 2. We're going to have a skinnier ellipse here. That's fine. Still got to find that foci points. So again, c squared equals a squared minus b squared. Big minus small. 25 minus 4 is 21. The square root of 21. Well, we'll leave it as plus or minus 21, but for graphing purposes, we'll go find a decimal representation saying it's just a little bit past 4.5. So from the center up 1, 2, 3, 4, ooh, really close to those vertices. If there is no graphing to be done and you still have to find the vertices again, start with the center, add and subtract the a value to the y coordinate. There's your vertices. Co-vertices, start at the center, add and subtract the 2 to the x-coordinate. There's your co-vertices. Foci, starting at the center, add and subtract the square root of 21, again, to the y-coordinate. And that would be my coordinates of the foci. All right, I'm going to stop here because I think the video might be getting a little too long.